Hello and welcome to the next session of the Big Data Conference 2000. My name is Jan-Willem Middelburg and I'm going to be your moderator for this session. And after I will do some introduction of the speaker, you can get all of your questions around this session into the Q&A box. You're probably familiar with the format right now. So if you have any questions, please use the Q&A box and not the chat. It is my great pleasure to introduce to you today Marta Paes, who you might have seen before because she was also a moderator yesterday. Marta is a senior developer advocate at Materialize and was previously a contributor to Apache Flink. Finding her mojo in data streaming and community work, she worked as a WH engineer for 4+ years at Zalando and Accenture. Today, we're going to hear Marta talk about an introduction to streaming SQL with Materialize. Personally, I'm looking very much forward to this session because it's a topic very close to my heart. So without further ado, I would like to extend a very warm welcome to Marta. Thanks, and take it away, Marta.
Thanks a lot for the introduction, Jan. And hello, everyone on the other side. Thanks a lot for joining the session so close to the end of the conference. Again, I'm Marta. Today, I'll be running you through an introduction to streaming SQL with Materialize, which you may or may not have heard about before. I would like to start by saying that I'm not going to rock your world with some completely new query language. Everything that will be discussed and demoed in this talk uses the same SQL you know and have used since the beginning of times. That means that if a statement like this makes any sense to you, you also already know how to write SQL that runs on streaming data. But this would be a pretty short talk if it was just this, right? So what I'm hoping to get across today is that it's possible to build streaming applications using nothing more than SQL, which I'm sure that you and many of the folks that work with you are either already using or can easily ramp up with. Let's start from the very beginning, work through some of the familiar ground to make sure that everyone can follow along and understands how we get to a point where the idea of using SQL to handle streaming data makes at least some sense. So the first step is to think about an OLTP engine or your traditional relational database from back whenever databases were invented. And the systems are designed for high concurrency, lots of reads, lots of writes, and transactions happening at the same time. And in general, they work very hard to make sure that your business data is consistent and available. But because OLTP engines are also kind of good, or at least good enough at other use cases, it's not uncommon that they're used as a one-stop shop that can also answer questions that you have about the data you store in them. So if you use a database, say like MySQL or Postgres, to store your product stock and orders, for example, you might be running some analytics on it. Maybe you're building some dashboards around it, or you're just monitoring what's going on in the system and so on. And this might be fine. Maybe your data volume and speed aren't that high. Maybe you don't have that many users concurrently accessing your system either. At some point, though, it's likely that this stops scaling well or it completely stops working. After all, these questions that people want to hit your database for are potentially very expensive. And this will start slowing down your OLTP database and kind of heating it up to the point where it starts kind of affecting its primary use case. Your read and write throughput might go down, your database may become completely unavailable, and suddenly the idea of using a single database for everything starts losing a little bit of its charm. But the problem is that these nasty workloads that are really eating into the performance of your database are really exciting and valuable for the business. So folks kind of still want to use them. And what do you do now? The next step might be something like offloading these workloads to a second database that is built in a way that is a bit more friendly to this kind of analytical loads. And this is usually an OLAP store where you don't have the same strict requirements for concurrency or availability, but you have others that are also really tricky to support, like very complex, large transactions, multi-way joins, subqueries, aggregating data over huge collections of historical data, and so on. And this represents a totally different set of things that your system needs to optimize for. So at this point, we have two types of databases. We have the transactional processor on one side, holding the source of truth for your data, and the analytical processor on the other, dealing with these complex questions that you want answered about your data. And because, like I said before, they have different things they have to optimize for, these two types of systems also end up with completely different designs. So OLTP systems are generally row-based, which makes them really, really fast for writes, but slower for reads that involve more than just fetching a row or a set of rows. And OLAP systems, on the other hand, are columnar, so the data is organized in a more analytics-friendly way that makes them really, really fast and efficient at serving ad hoc requests, like the ones that your users wanted to run before on your OLTP database. And overall, in comparison to the scenario we had before, things cool down a bit, at least for now. But of course that at some point there will be fire and flames again. And as the users of the OLAP database get very greedy and start asking more complex questions or asking questions more frequently, now it's the analytical processor that starts blowing up. So the problem isn't really solved by doing this offloading. We just sort of pass the hot potato from one system to the other. Though at least, to be fair, now the impact is more on the side of the business stakeholders than on the actual availability of your actual whole business. And this finally brings us to streaming and Materialize. So if we think about the problem in a different way, let's call it online view maintenance, we can have our analytical system work in a push model, which is the opposite of just sitting around waiting to be queried. So what it does now is proactively listen for changes in the input data, maintain the results for questions it knows that you want to ask repeatedly, and keeps whatever you have downstream fresh without doing unnecessary work or without you actually having to interact that much with the database. So for example, if you have a dashboard, any changes will be pushed to it instead of having to repeatedly pull the database periodically to see if anything changed. In practical terms, this just means that you can tell the database, hey, I'm interested in asking this question over and over again. Can you please just pre-compute it for me as the data changes so I always get correct and fresh results without actually having to worry too much about it? In this way, we kind of don't have to pretend anymore that we're surprised to get the same query for the 100th time. The processor can just go ahead, incrementally do some amount of work and be proactive in maintaining the results instead of calculating them from scratch every time based on a snapshot of data that might not even be that fresh anymore. So to kind of sum up this introductory part, and in short, Materialize is a database that is just purely optimized for view maintenance over streaming data. So data that is constantly flowing, constantly changing. We're calling it a database because it walks and talks like a database, like you will see in the demo soon. And it still supports all these heavy, crazy workloads that we wanted to run before, with another big difference, which is that it can ingest data from multiple types of sources, including sources that produce data that might not even ever fit in a relational database in the first place. So you can then take all of this data, define some transformations just using SQL queries, and Materialize will just efficiently maintain the results for you as the input changes. And the other idea is also that you can put these results to work immediately, either by directly connecting it to BI tools. You can just sync it to Kafka for event-driven use cases, or you can stream it to applications interactively. So like if you have a Python or a Node application, you can just stream your results right out to the browser, for example. So this was a lot of talking. Let's actually get our hands down and see a real world example, kind of, that hopefully sums up all the things that I've been blabbering about for 10 minutes now. So what I brought to you today and what we'll be looking at is data streaming in from Twitch, which is the biggest live streaming platform on the internet these days with around 15 million daily users. And it's especially popular, so this is what we'll try to tap into. So I really apologize in advance for putting together a meta demo that analyzes streams of streams, but hopefully it's not too confusing for everyone on the other side. So the whole setup will be running on Docker. It's available for you to try on GitHub. I dropped the link on the slides. I'll also drop the link in the chat after the talk. And if you wanna give it a go, all you need is some Twitch tokens that don't take a lot of time to get. And what the setup is doing is basically putting together an end-to-end analytics pipeline that grabs active gaming streams that are streaming right now on Twitch from the Twitch API, and it kind of trickles it down to a live dashboard that is being updated in near real time. So we have quite a few services involved. So let's start with our sources of data. We will be having data coming in from Kafka and Postgres. So for Kafka, there's a data generator that is just a small Kafka producer written in Python that is fetching data from the Twitch Elix API. Postgres, on the other hand, will just hold some reference data to enrich these events. And then we have Materialize that we will use to kind of ingest and bring using SQL. And we're finally just dumping everything into Metabase to just visualize whatever we have been maintaining in Materialize. And I know that this sounds like a lot of moving parts because it is. But if you're looking to get started with Materialize, you can just locally install it. So if you're on a Mac, you can just brew install Materialize. And you can do a much simpler Kafka-less even streaming setup going in just a couple of minutes. So to get started, we can bring everything up, make sure that all the services we expect are nice and healthy, and that the Twitch streams Kafka topic was created and is getting data from the Twitch API, which is what you see coming across the screen right now. So things work, good news. We're able to ingest data from Twitch. And if you look closely, which you can't really hear, each of the records for an active Twitch stream will have one or more tag IDs. There are just, in Kafka, they are just meaningless UUIDs. And the mapping of these IDs to actual human readable tag is what we have stored in Postgres. So that's what we'll use later to enrich the events and make them a bit more meaningful using Materialize. Okay, so we're now ready to enter Materialize land. First things first, we need to tell Materialize where to find this data that we want to consume. So the way you do that in Materialize is by creating a source. In this case, we'll have a Kafka source consuming the Twitch streams topic that I was mentioning before and that you saw being filled up with data. And the problem with the source data here is that we'll get multiple events for each key or for each stream as viewers join and leave the broadcast. But we're only interested in keeping the most recent one. So we need to tell our Kafka source to work in upsert mode so that you can do insertions and retractions to make sure we only ever keep the latest values for each key. Okay, and with that out of the way, we move to Postgres. So we're going to connect to Postgres directly and do some change data capture. And the idea of using the source is that in the real world, the list of tags on Twitch is maintained by Twitch, the company itself. So in the real world, it would make sense to ensure that whenever someone from the Twitch team changes this list, say someone adds a new tag or some tag is deprecated or they just change the description of a tag, we will instantly push this change into Materialize. And if you're familiar with CDC, we of course could also have done this with Kafka and Debezium since we're using Kafka anyways. But I wanted to show an alternative way in case there are people listening that don't run Kafka at all and just want to connect to their Postgres instance. So to run these DDL statements in Materialize, we first need to connect to it using some sort of SQL client. Like I mentioned before, Materialize looks and feels like a database. So one way to connect is to just use a SQL shell. Here I'm using the MZCLI mainly for convenience, which is pretty much equivalent to the pSQL client. But you could use something like dbeaver or datagrep to issue these statements as well. And as soon as we run our create source statements, we can do a show sources. And you see that the two sources we created have been persisted in the Materialize catalog, which is good. So I just want to point out that Materialize is not consuming any data yet. We're just telling it where to find what we need when we actually need it. So there are some intermediate steps in between this and what's going to happen next, just to make sure that the data is in the format that we need to consume it. I don't know if you noticed, like in the create statement, we are ingesting data as raw bytes because in Kafka, these are JSON formatted messages. So we need to do like some pre-preparation that I'm not going to bother you with. You can check the whole thing and run every single query or every single statement on GitHub from GitHub afterwards. And cool, now that we have our sources, from here we can start thinking about all the questions that we want to ask from this data. So rule of thumb in Materialize is that you create what is called a materialized view for any questions that you want to see answered repeatedly, but fast. So let's start with, for example, figuring out what's the most popular games that are playing on Twitch. This will be based on how many viewers are currently watching. And for this, we just need a simple aggregation based on the game name. And then we get the number of streams that are currently active for this game, and also the aggregated count of viewers that this active stream has right now. And then we'll be able to start asking questions on top of this materialized view that is just maintaining whatever results of the query it has embedded. So you can ask something like, what are the top 10 games being played? And you can do specific lookups. So you can check if anyone is playing Doom right now, or if no one actually cares about Doom anymore. And you can do this with a simple select star on top of the view that we just created. And in both cases, because you are just reading out the results that are maintained in the materialized view and not really doing any computation, this will always be pretty fast, kind of like in the millisecond range. And you can see here that creating the materialized view is pretty fast. And by this time, we haven't really fully iterated the stream yet. So we have just started the process in so that when we hit the view, the Materialize view with random queries like the ones I showed before, we can get the results really fast. So when we use this view to find out what the top 10 games being played are right now, Materialize has always the freshest results at hand. So if you reissue the query over and over again at different points in time, you'll see that the results are changing as new data is streaming in from Kafka. For example, if you see the viewership count of just chatting, it's a bit imperceptible like this. It would, of course, be easier to see over a longer period of time, but you get the idea. So the point is that Materialize is now maintaining these aggregated counts for the number of streams and viewers for each game. All these results are being maintained in memory as Materialize receives new data. So any query on top of this view, like I said before, and like you can see here, will return within milliseconds. And it's important to note that we're not at any point rereading the source data and recomputing the results every time we issue a query. We are just really reading out the answers, which has like really very little overhead on Materialize itself. And you're only storing as many records in this Materialized view as you have games with active streams. So this means that you can also do lookups based on this in-memory results, like I was showing before when you wanted to ask if anyone was playing Doom. This is just kind of digging into this index that Materialize creates to maintain the data next to this is all we need to store. So like in reality, we are only storing three different fields. Materialize will just make sure that the results for these 3 fields are kept up to date. Yeah, and like I was predicting, not a lot of people seem to be into Doom right now. We just have like a couple of streams. But anyways. Okay, so we haven't really seen anything groundbreaking so far other than just introducing a bit like the way that Materialize works, which is a little different to everything else out there. We're just doing streaming using SQL, just using a fairly straightforward aggregation, so no special magic here. We're going to look next into a couple of new patterns that SQL can provide when it's used on streaming data. That you might assume that you would need a more advanced, not advanced, you might assume that you might need to go into a different kind of stream processor that supports some kind of imperative language, or that you would need some custom SQL extensions to actually achieve. And I'm going to show you that you can do it without ever leaving the domain of standard SQL. So starting with one of the more immediate things that is different in streaming is that time keeps ticking along. So time is moving as it is moving as I'm sitting here. So unlike what you might be used with batch, for example, where your data is kind of frozen at query time. And this means that, for example, if we want to ask a question like, what streams have started in the past 15 minutes? This, in the past 15 minutes, in streaming is a moving target that changes as time progresses. So how would you express this in SQL? So in Materialize, you can use something that is called temporal filters to define a sliding window that will expire any event that progressively falls outside this 15-minute window, and it will pick up new ones along the way. And the real differentiator here and what's new and kind of refreshing is that you don't have to learn any new syntax to actually define time windows on streaming data here. So as you can see, this is defined just as a constraint in the where clause. The key here, and what might be new for you, but you will see it's not that new either, is this function called mz logical timestamp, which keep tracks of the logical time for your query under the hood. And if you want to make a parallel to the relational database world, this acts kind of like the now function would on Postgres or MySQL, but applied to streaming. So if we run this, it will return all the active streams that satisfy this condition of not having started more than 15 minutes ago. And you can see that Materialize is doing its job if you select the minimum started date that is stored in this materialized view, which should be moving forward as time progresses, as you can see. And as this happens, records are expired and new records are illegible and brought into the view. And this is, again, all handled by Materialize. All you need to do is define the Materialize view and whatever you want it to maintain for you. Another interesting pattern, and this is a known challenge in the streaming world, is doing joins between multiple streaming sources. Like in our case, as I mentioned in the beginning, we need to enrich the events that are flowing through Kafka with the reference data that we have flowing in from Postgres. So because the Postgres source is doing CDC, imagine someone at Twitch actually changes the information about a tag. Again, that would be shipped instantly to Materialize, and we would reflect the changes in the results of the join that are linked to that tag. And because we're working in the real world and data is mostly never beautiful and ready to be probed, each active stream can have multiple tags, of course. So we can also just unnest the array that has this collection of tags for each event, and we can pre-aggregate the results to make the join a little bit less expensive, though Materialize is pretty efficient at maintaining streaming joins resource-wise. Okay, so if we run that and we create our Materialize view, we then can, for example, get the 10 most popular tags by just doing a select star with an order by and a limit clause. And this top 10 right now, is LGBTQA as the most popular tag, Portuguese following, because I was running this specifically for the Brazilian Twitch community. And this top 10 will change for sure as new events flow, as I mentioned so far. So whenever a new game becomes more popular than any of these games, or whenever a tag gets incremented, the number of times that it's used within Twitch at a certain point in time, the top 10 may change. And again, if you run this query multiple times, you will see it change over time. So the last pattern I would like to point out, even though it's a bit more complex and it uses something that I think is even for Postgres users, it might be esoteric enough that they haven't heard about it either. So what I wanted to mention is this ability to do event-driven queries. So it uses lateral join, which is the easiest way I found to explain it is that it's like a for loop, but for SQL. So let's say that we would like to know who the most popular streamer is for each of the top 10 games on Twitch right now. So if you remember, we wrote a query to yank that top 10 out on the first ever Materialize view we created here. What you can do is use the results of that top 10 query and pass each game there as a parameter to the body of the lateral join to only run the subquery that we have here that is getting based on the viewer count for only that subset of games that is within the top 10. So what this means is that you can have an arbitrarily complex SQL query inside the lateral join, and it will only ever be executed for the subset of inputs that you're passing it from this other view. So here you can see that we're doing the join inside the lateral join body. We are using a field from our top 10 view to actually do the join with the Twitch stream with this other view that is calculating the top streamer. So, okay. Maybe let's see it in action. Maybe it makes a bit more sense. So in our case, this will only ever maintain 10 results in memory. This is all the memory that it's going to occupy and Materialize. The streamer with the highest current viewer count for each of the top 10 games. And if this top 10 ever changes, which it probably will over time, Materialize will only do work on the subquery for whatever new game makes it to the new top 10. So this gives you a way to express a dynamic top 10 over streaming data, which is admittedly very complex to explain, but it's pretty cool. So if you have some time and you are interested in this, I really recommend that you read a bit more about how event-driven queries work in Materialize. It's pretty cool. And to finish the demo off, you can just basically visualize the results of all the questions we just threw at Materialize using a BI tool like Paes, which is an open source BI tool that I think is very popular right now with the modern data stack. And again, because Materialize presents to the outside world as a Postgres compatible database, like I will explain in a second, you can connect it to pretty much anything that has a Postgres driver, like we are doing here. So, leading into the final part of this really long talk, what's the big deal about Materialize? Why is it different to any other solutions out there? Why should you care? The first point, there are 3 different points that make Materialize different to other streaming systems. The first point is that it uses standard SQL. So going back to the initial spoiler slide, you can think about your computations in the same way that you have for decades. And you can even migrate existing workloads that you might have in a relational database with minimal modifications. And most importantly, you don't at any point have to learn new syntax or semantics that are not part of the SQL standard. It also allows you to run complex analytical workloads using any type of join. Like I said, this is usually more restricted in other engines. In Materialize, you can even run non-windowed joins, use arbitrary join conditions. There are very few rules, actually. As well as use exciting patterns like we saw in the demo with the lateral join. And Materialize has really been built, or whatever is underneath Materialize is really hardened to handle 8-way, 16-way joins if you feel like it. And it fully supports the TPCH benchmark. So you can run data warehouse grade queries on it, and it will not fall apart on you. And with the added bonus that Materialize also doesn't really care if you're doing batch or streaming. You're able to mix and match and, for example, backfill your streaming pipelines with data stored in S3 just using a simple union. The second differentiator is something that I've already mentioned a couple of times along the talk. So Materialize is Postgres wire compatible. So it's sometimes scary how much it looks like you're just talking to a Postgres database. You can run it on a single node. You can connect to it using SQL shell or a SQL driver in different languages. And because of this PG wire compatibility, you can also easily integrate it with existing BI tools like we saw with Metabase and others in the future, like Superset, once we do a bit more work on our catalog. And for me, as a previous data warehouse engineer, that was kind of used to sometimes actually seeing what I was doing. This is a really cool add-on to the streaming systems that you have out there that don't really have this feature. And most importantly, it also fits the part of the modern data stack. So you can build with your usual tools without adding complexity to your stack. So you can use Materialize, for example, with dbt. So even if you're not into distributed systems and you're an analytics engineer and all you want to do is use SQL, you can integrate Materialize with a lot of the tools in the modern data stack. And finally, the secret sauce at the heart of Materialize. So what's really at the core of it is differential data flow, which is Materialize's engine. It makes sure that Materialize only ever does whatever work is necessary. So if somebody submits a query and very little has changed with the new inputs, Materialize will actually not do a massive quantity of work. It will just do work that is proportional to how much the input data is changing. And it's based on timely data flow, which is backed by many, many years of research led by Frank McSherry, which is one of our co-founders. And it borrows some techniques from traditional databases like shared indexes that make Materialize's engine very resource efficient. And it allows you to still, despite all of this seemingly complexity and academia background, you as a user only have to care about what queries you want to run. And then Materialize handles all the hard parts of translating that into optimal data flows and this kind of thing. So the best part of Materialize's engine is that as a user, you're completely abstracted from it, and you don't really need to learn about it unless you really want to. So to wrap it up, is Materialize for you? Of course, depends on a lot of different factors, but as a overgeneralization, if you need the benefits of moving to a more real-time streaming architecture, but you don't want to give up on the creature comforts or of your beloved databases, then maybe you should try it out. And if any of this made any sense or any of this sounded interesting to you, you can join us on Slack. I also dropped the link for our Getting Started guide, which I promise is like way simpler than the demo that I was showing. And you can also check our commercial product, Materialize Cloud, if you don't want to run Materialize yourself. If you do, Materialize is source available. It's free. You can run it on a single node by yourself without ever talking to a salesperson, which is admittedly also nice. Thank you so much. That was it from my side. I hope you enjoyed it.
Good. Well, I definitely enjoyed it. I thought it was a very cool presentation. So thank you so much for that. I absolutely learned a lot of new stuff. And I'm pretty sure other people have tons of questions as well. So before we get started with the moderation, just wanted to say a quick thank you. I think this was a very excellent and very insightful presentation. So thank you so much for that.
Thank you.
Good. Let me get started with looking at some questions because time is going to be limited. And one key question that came in from AJ is how is Materialize different than KSQL?
Mm-hmm. So I think this is probably the most common question people have because, of course, Materialize is very obviously in the same or in an approximate bucket to KSQLDB and Flink SQL, for example. So I think there are a couple of different things that you can mention here. And again, I don't like to be too pro one tool or the other. I think, depending on your use case, depending on the know-how of your team, budgets, etc. I think really what distinguishes Materialize is all of the points that I was saying that KSQL doesn't really have. So KSQL does not use standard SQL. They have their own flavor of SQL. So this means that you would not necessarily be able to transfer your existing knowledge and your queries. You probably would need to ramp up a little bit and learn the syntax of KSQLDB. Another difference is the ecosystem. For example, like I was mentioning, that you can use Materialize with dbt. This is not true for distributed streaming systems like KSQL or Flink. They're a bit more in the ecosystem that you really have to be a data engineer or a distributed systems engineer to really be able to even use it with SQL, because someone has to maintain all this infrastructure for you. And Materialize, you can just, it runs as a binary, so you can just install it like you would install Postgres. And you can connect to it with any of the tools that you maybe already use. So like I was mentioning, the Beaver and Data Grip. And if you have like your if you have some applications that were talking to Postgres before, you can just like very easily just plug it in to Materialize with a PG driver, and more. Yeah, and in the end, like you should go into the Materialize blog. Like especially Frank has really fascinating blog posts about how timely data flow. So like the core engine of Materialize is very fundamentally different than KSQLDB or Flink, for example. It's really, really interesting, and that's why with Materialize you have less limitations. You can actually do joins with unbounded data sets, where, for example, in KSQL, you're usually limited to having to you're kind of forced to apply time windows on your data so that you can actually perform joins that that actually run.
Good. Well, I think that's a very clear answer, and also already a very detailed one. So another very interesting question is basically what triggered me during the presentation is, in data streams, one of the major topic is always variability. So what happens if there's this peak load? Let's say traffic is not going to be just, it multiplies by 1,000. So is Materialize able to deal, and if so, in what way, with these kind of peak loads that you typically see within streaming data sets?
Mm-hmm. So I think there are two sides to the answer to your question. One is that if the peak varies a lot, but actually the data that isn't affecting the results that you're looking at, Materialize will only do the minimum work that it has to do to make sure that whatever you asked is maintained. So like if you have a peak load, but it doesn't really affect the results of the query, the specific query that you materialized, it doesn't really make a big difference. Operationally, of course, right now, I mean, Materialize can scale up right now, like it runs. It doesn't run distributed yet, even though Timely is built for running like highly distributed horizontally. But Materialize itself doesn't have this feature yet. We're kind of working on it. Also, in the of course, in the cloud product, this is one of the main appeals of going to the cloud, is that eventually you can horizontally scale to handle peak traffic. But the thing is that also with Materialize, because of Timely and how it does resource management, you also can kind of sustain a lot of times a bigger load with less usage of resources. So I would say that, of course, operationally, I think we are still getting there. But really, I really urge everyone to go read Frank's blogs about how resource management is done in Materialize. It's just really it's really fascinating. So yeah, that would be my answer with like the two sides of it. So work in progress, and also Materialize kind of is very resource efficient. So maybe you get a bit more bang for your buck, just like with a smaller instance, for example.
Well, that's absolutely and definitely an answer to my question. I also think a very good one. So I will definitely start reading those blogs and see if I can spin up a small instance of Materialize myself.
Yes, please do.
Good. Last key question I see just coming in like 1 second ago. So give me 1 more second. Is would like to ask if it allows for scheduled procedures.
So this is an interesting question, because in streaming you don't really need to schedule procedures, right? I guess that yeah, I guess that because things are always on, and it's the processes in Materialize are just running all the time. You don't really need to schedule anything. I mean, I think we've had this question from users before, especially users that want to backfill their jobs in periodic intervals of time. And right now, I don't think we have a good answer for this. But, you know, if you want to maintain things over time without having to worry about scheduling things, that's kind of the point of Materialize.
Yeah. Good. I think that's a very quick and very thorough question. It was absolutely a pleasure to moderate this session. So thank you so much, Marta. It's really, really good. We're out of time, unfortunately, so I have to end the session. But thanks so much for your wonderful presentation today.
Thank you, and everyone watching. If you have any questions, you know, just hit me up. I'll be around.
Absolutely. We're going to be stalked.
Yeah. Thanks again,
Thank you.
yeah, also for moderating.
Bye-bye.
Bye, everyone. Whew.